Hello and welcome everyone to our webinar Acoustic Simulations Powered by the Cloud. My name is Jukka Knutinen and I'm the head of marketing at Quanscience, where we have a cloud-based FEM multiphysics simulation software called Quanscience also, which we'll use for today's demonstration. Before going further, I'd like to inform you that this session is being recorded and we'll be sharing the recording with all the registrants after the event. To begin, let's quickly go over our agenda for today. In the first few minutes, so very soon, we'll go over the motivation for this webinar, after which Dr. Abhishek Desmuth, one of our application engineers and the technical speaker of today, will take over and guide you step by step through the main course of today, which is the 3D loudspeaker simulation. While we're waiting for the simulation to run, we'll take a look at some other relevant cases from before, as well as explore some other, perhaps not so obvious benefits cloud computing can offer with regards to acoustic simulations from both the technical and business perspectives. After going over the results and visualizations, we'll have a Q&A session with Dr. Desmuth. If that sounds good to everyone, without a further ado, let's go over why exactly we're here today and what we're trying to achieve. So many of you as acoustics engineers dealing with simulations might have encountered some of the issues that arise from the limited computational capabilities of desktop-based simulations, namely long runtimes of hours or even more, the need for simplified models, and these simplified models causing simplified results. For these problems and many others, as we will see later, but these being the biggest, utilizing distributed memory and computation, such as with cloud-powered simulation tools like Quanscience also, can provide not only more accurate models and therefore results, but doing this much, much faster. How many iterations more could you do when the simulation runtime is no longer hours, but mere minutes? How many iterations would you even have to do when you don't have to make compromises with your model and can compute much larger models with more accurate results? How would this expedite your design and R&D processes as a whole? Well, I'll pass the microphone to my colleague Abhishek, who will show you in real time how setting up a simulation with tens, if not hundreds of millions of unknowns looks like, and how a simulation like that can be solved in a matter of minutes. Again, thanks for joining us today, and we hope you find this webinar at the very least informative, but hopefully even eye-opening. Go ahead, Abhishek.
Yeah, thanks, Yukka. My name is Abhishek Deshmukh. I am application engineer at Quanscience and also leading the team of application engineers here. I'm quite excited today to be able to present this demonstration of our product in this webinar. More specifically, our acoustics capabilities and so on. So, as Yukka said, we can offer solutions to speed up your simulations in some cases even speed up even enable your simulations. So basically large scale simulations which you probably cannot perform on desktop softwares, we can do that. Without a further delay, let's jump to the product demonstration. So our product Quanscience AllSolve is a browser-based product. So all you have to do to access this is go to the URL allsolve.quanscience.com, input your email address, password, and then you are in, and you will see this screen as shown here. So on this screen, what we see is several projects. There are also demo projects which you can start with, and in this webinar we will start with a new project. So let's start with create new project. Let's name it acoustics webinar. So to start with, we can either upload a geometry, which is we offer different formats. For example, step file format, which is standard CAD exchange file format, and we also offer GDS file format for specifically for MEMS devices which are designed in some specific softwares which export these GDS files. Apart from that, you can also create geometry, simple shapes in the environment, in our environment as directly. So in this case, I will import geometry which has been setup, and it's loading. And yeah, this is basically a layout from a living room. For example, some objects in the living room that you can find. And as promised by Yuka, will present the loudspeaker simulation. So you can see two loudspeakers on the one end, and some sitting arrangements and so on. So we can see that the geometry, I mean, we can activate the dimensions. These are to scale. I try to keep it as much as to the scale as possible. And yeah, it's not aligned to the axis because when it was created in FreeCAD, it's aligned to origin at this corner. So I will shift this geometry uh, to make the origin to the center. Yeah, now it's aligned to the center. We can have a top view. And yeah, uh, then we have to create for acoustic simulations, so we have to create some air box around it. So let's create a sphere. So as I said, we can create simple shapes here. For example, a sphere. In this case, I have to shift it a bit to adjust to my domain. You can fit to the window. You can see that that's the sphere shifted downwards. Then I will create a box to cut it from below. So you can make also, you can see the transparent view. And the box is, let me check, shifted by this 20. So you can see it's touching almost the ground. So it's, the sphere will be cut from below. So let's fragment this. So fragment all, it's the operation that creates the volumes which are not intersecting with each other. So basically creating disjoint volumes, so that later we can delete what's not needed. So I will remove the volumes that are not needed. So to select that, I use a bit different method. So I first hide the volumes which I want to have. So there are three volumes I would like to keep these, and that. And then I would select the all other visible volumes. So this is kind of complementary method, so that it removes everything else and keep what you need. So yeah, that's the domain of interest that we have here. And let's make a single volume out of this. So you can do some boolean operations as mentioned here, as shown here. And yeah, let's make a single volume. So with this, we should have our domain of interest. And yeah, ideally you can go directly from here to the further steps. But I would like, when you run these kind of large simulations, you don't want to dump all the 3D data. So I would like to uh, write the data on some surfaces which I would like to create here. So let me create some box which will cut through this volume. um, yeah, so just shifted by 1.5, and another box which is shifted in y direction. Yeah, so basically these boxes. And then again, fragment. And last step is remove what you don't need. So in this case, I don't need these volumes. So basically, these volumes. So what happened with these operations are, you can see the volume is split into several volumes again. So one volume was split into several volumes, and I get these surfaces which I can later use for writing the data out uh, to visualize. Yeah, so that's all about the model. So to save some time, let me quickly go to the meshing. I will come back to uh, that later to explain, but let me start the meshing right away to save some time. Yeah, so we have a workflow which is quite simple here: model, properties, physics, and simulation. So we already built a model, or rather imported and modified it for the simulation, and now it's time to assign the properties. So for example, uh, we want to have air in this domain. um, let's select all volumes, because these are all air volumes. uh, you can also add, so we have a bunch of materials in our library which you can pre-select, and you will have those material properties available. Or in one case, or in some cases, you want to define new material, and this you can do this simply by adding new material, and then you get then you have to define the properties yourself. So we have list of bunch of properties, and yeah, you have to define then relevant properties as needed. In this case, we don't need a new material. We just want air, and we can see the properties that are available. So for example, density, these are properties at 20 degrees Celsius, and atmospheric pressure. uh, and you can see that we can also define anisotropic properties by just clicking on this checkbox, and and so on. And one thing I would like to point out is this symbol here. So that means the properties can be also function of a field. So for example, if your density is function of temperature, you can simply add a expression here which is function of temperature, and yeah, later you will have it as a function of temperature. um, that's all about the um, properties. We have here so-called shared expressions, which are kind of global variables which are accessible throughout the simulation. So for example, in this case, I want to define frequency as the shared expression. I will give some value to it, and yeah, later we can use this for parameter sweeps, and also other places, for example. And as I said, I wanted to visualize data on certain surfaces, not the full volume. So time to create some individual surfaces. um, Let me name them. For example, visual. um, I want to select, so I would like to hide some surfaces which I don't need here. um, there's one more surface, yeah, and then select all visible surfaces. So that's the surface that will visualize the pressure fields later. Then we can also create some planar surfaces, for example z plane, which I created before. um, so basically this surface, and that's it. So we have defined our surfaces now, and we can move on to physics tab. So in this case, we can add new physics. So here we have list of different physics that we offer currently. So in this case, we select acoustic waves. Um, Once this is selected, the default is applied to the whole geometries. If you want to select certain volumes for specific physics, that is possible by selecting individual volumes. In this case, I want to apply for all volumes, so that's I keep it default. Then we would like to apply some boundary conditions, for example, pressure source. So in this case, let's apply the pressure sources to these loudspeaker diaphragms. So select surface, um, that's one loudspeaker, and the second one here. Yeah, that's it. And we have to apply some signal here. So SN1 means sine 2 pi ft. So 1 is the first harmonic, and that's the signal that. So we are going to use we are going to simulate harmonic analysis or frequency analysis. So that's why I apply this boundary condition. Then uh, yeah, on the outer surfaces, so we want the waves that are sound waves to leave the domain. So for this we offer perfectly matched layer. We just need to select the outer surface here, and that's it, and apply, and we you have the PMLs on this layer. I would increase the layers a bit here to help me damp those waves, and it's not necessary, just for, yeah, increased convergence. Once we have set up the physics, that's it. Don't need to do much here. We can go to simulations tab. Meanwhile, our meshing has finished already. You can see some metrics of the meshing, nodes, elements, and you can also preview the mesh. Yeah, so this is quite reasonable mesh for this. And as said, we come back to this. So we have quite extensive meshing control that you can define here. We have mesh refiner. You can define your mesh sizes, minimum, maximum. In addition to that, we have also structured meshing possibilities for simple shapes. And you can also do, let's say, mesh refinement on certain regions. So if you want to refine certain volume, not the full region, you can select volume and add that volume there. So, and yeah, you just go there and select the volumes. But in this case I will keep it simple, uh, minimum, maximum size, and that's the mesh that we are going to use. um as for the simulation controls, so let's name this as PMLs 100, because I'm going to use 100 cores in this case. And we have to select harmonic analysis. We also offer other types of analysis, which I will come back later. In this case, let's, as I said, we can use these shared expressions as anywhere in the simulations, wherever you see this symbol. And yeah, that's all we need to set up. um, we can select from different machines that we have available on the cloud. And I would select one CPU 16 gigabyte machine and hundreds of these machines. And you can set the timeout duration. Yeah, and then you to visualize, we have to create some output. So for example, here pressure field, we just want to visualize second harmonic, and we write the data on skin only. And once we have set this all up, you get this fully automatically generated Python script. This contains all the elements that were set up using the GUI. And what you can simply do is click on this, change the mode to edit, and yeah, you are uh, good to uh, good to edit the script. In this case, I would like to change some tolerances. We don't need to have such tight tolerances. We can get 3-digit accuracy with 1 e minus 4. And other thing I want to change here is I want to apply the region which I defined before. And similarly also create another output for Z plane, just, and yeah, just like that. uh, this is all set up now, so we are good to start the simulation. And that's all. You have 50 lines of script here. Let's start the simulation already. uh, and while this simulation is running, you can already make a copy of the simulation and change this to, so go back to your setup, delete this. I will use now absorbing boundary conditions, which is another type of another way of specifying the um, the boundary conditions at this outer surface, which allows or which prevents the reflections. So let's select this surface again. That's it, and go back to your script and just refresh the script. And now this is updated with the absorbing boundary condition, uh, basically, yes. And we can copy some elements. Before that, you have to save the script. You can copy some output elements from the previous script as it is and just paste them here. uh, and that's all. And let's name this absorbing boundary conditions, and this will run also on 100 nodes. And let's start the simulation. And while this is running, I would like to make another copy of this simulation. And now I'm going to set a big simulation, so 500 cores. So this was rather I would say to some extent coarse mesh. So in some cases you would like to use even finer mesh, depending on the uh, conditions and so on. But all can also do order adaptation. So without changing the mesh, you can just increase the order of the fields here, and you get higher accuracy. And while you change the order, we should also output the fields in the same order. Here I would not go for fifth order, just to avoid the large data which we uh, yeah, basically we want to visualize. Yeah, once this is done, let me choose 500 nodes and apply, and hit the start button. And that's all. So all our three simulations are running now. And while these simulations are running, I would like to go through some of the multiphysics capabilities, and some case studies. So let's switch to, so that's just, I mean, this is to just say that it's not just acoustics or simple acoustics problem that we can do, but we can also do multiphysics simulations. Depends on the level of detail you want to go into. For example, here I am simulating a loudspeaker cabinet with all the elements that are required, for example. So let me hide the volume. So that's the cabinet with a resonator, and yeah, so that's the loudspeaker driver. And you can see that it has all the diaphragm, the spider, the permanent magnet, and also the voice coil. And all these have been assigned proper materials and material properties. um, yeah, this has been assigned, and yeah, we can do all kinds of physics coupling. For example, in this case, I have added solid mechanics, current flow, magnetism, and acoustic waves. So what happens is that current is driven through this voice coil, and as the current flows through the voice coil, it creates a magnetic field which is interacting with the magnetic field of the permanent magnet. And this is coupled through this AV coupling, and this creates a magnetic force which acts on the diaphragm. So basically this coil moves in this direction, applies the structural motion to the diaphragm, or the cone, as it is called, through this magnetic force. And through the acoustic structure interaction, it is then transferred in terms of acoustic waves emanating from this loudspeaker driver, and that all of that can be set up fully coupled in this setting. And one thing I didn't mention this. So once this is set up, you can run the simulation. In this case, we ran multi-harmonic simulation, so which is also one thing I would like to point out. So this is the um, so why we need multi-harmonic simulation, because we are using current and magnetism, and which creates a magnetic force which is non-linear. And for non-linear cases, you might have harmonics appearing, or higher order harmonics appearing in your simulation, and that we can do quite easily. You can even select harmonics that you want to include, so there is no limitation that prevents you from that. For example, I could do simulation like this as well. So that's to highlight this, we are the only one, or we are in only one simulation platform that offers this in the world. And yeah other thing I wanted to point out was frequent parameter sweeps, which I didn't mention. So not just the domain decomposition or running the simulations on hundreds of cores, but you can also run many of these simulations in parallel. So basically doing parametrics or sweeps, for example frequency sweep in this case, and you can get uh, plots like sound pressure level versus frequency. um, with that being said, let's take a look at some visualization. Let's move to the slides. Yeah, so this is the results. These are the results of the loudspeaker driver in open air. So including all the physics, acoustics, solid mechanics, current flow, and magnetism. On the left, you can see the magnetic flux lines, and on the right, you see the isosurfaces of pressure, uh, low and high values. This simulation was run for 3 kilohertz on 35 minutes on one core. And we also ran a loudspeaker with cabinet, which I just showed you. This was 10 close to 10 million degrees of freedom for one and close to 1.5 hour on one core. You can also place, so once your simulation is done, you can place objects inside and try to interpolate sound pressure levels. So this is also possible here. In addition to that, now not just loudspeaker simulations, we can also do ultrasound frequencies. So for example, piezoelectric micro machined ultrasound transducers, as shown here, 5 by 5 PMUT array, uh, run on 50 cores. Then 15 by 15 PMUT array, 30 million degrees of freedom, 3 minutes on 100 cores. And last but not least, we can also do nonlinear frequency analysis using Westervelt equations. So that's about the case studies, and now over to you, Yuka.
Thanks, Abhishek. Before going over the other benefits that cloud computing can provide, I'd actually like to share quite an interesting story. So we were at this conference last year, and there was this clearly seasoned, highly skilled acoustics professional from one of the world's leading acoustic manufacturers giving a presentation about a problem they were facing with a certain acoustic simulation. If I remember right, it was also a loudspeaker simulation with approximately 1.5 million unknowns, and they had sort of begun to reach the upper limit of what their desktop-based simulation software was capable of running in a reasonable amount of time. Now, to tackle this issue, he quite ingeniously incorporated some boundary element method algorithms or some similar very fancy advanced technique to get the simulation to work in a feasible manner, although still with some necessary compromises. Well, after his presentation, our CEO approached him and showed him a similar case we have solved with Allsolve, with not 1.5 million unknowns, but 360 million, and the time to solve it, 15 minutes. needless to say, he was very keen on learning more. And this is the thing with the technical limitation imposed by the current leading desktop based simulation software, the engineers, you guys, have to either suck it up and keep on simplifying and waiting, or to come up with these ingenious, albeit complex workarounds. Our goal is exactly to remove these limitations and allow you to run the kind of simulations that you want, in essence, opening avenues for creativity where computational power and random access memory aren't a bottleneck.
Yeah, indeed, Yuka. I also remember one of these stories from MEMS transducers conference, where I was talking to a postdoctoral researcher who was developing these PMUT arrays, and what she told me that she was quite frustrated with the simulation times. So what she had to do was, she could only simulate a quarter of PMUT arrays on the desktop software that she was using, and it took almost a week for simulation of one frequency. And this is where we think that allsolve can basically speed up the simulations, as we have seen from PMUT case studies. We can do this in minutes, so you can save a lot of time uh, in your simulations using our highly optimized algorithms, which are specifically designed for HPC and utilize the cloud resources.
Yep, but as I sort of promised, the speed and scalability is not the only benefit that can come from the cloud. So let's go over some of the other benefits that can arise from either the cloud inherently, or more specifically Quantside also. So one of the more cloud inherent benefits are the collaboration benefits. Anyone who has used a cloud-based tool knows that the collaboration possibilities are at best as easy as sharing a link. And with also that is the case with these simulation files. So basically, when an organization gets access to the tool, there are no user limits. So everyone in the organization can use the software even at the same time. So sharing a project is literally as easy as sharing a link. There are no version incompatibilities. All of the files are always up to date. And well, as a small but annoying thing, there is also no professional courtesy required when sending these files over email. Uh, what else? The pricing. Well, there's a lot of flexibility there, and the exact pricing, of course, for a tool like this is almost always a custom one. Basically, depending on the need of the company, the number of parallel cores they require, the number of core hours, etc. What I can say is that the plans that we have are extremely flexible and tailorable for the needs of both small startup with limited simulation needs, as well as to international conglomerates in need for a lot more. Also, as a multi-physics platform, all the features are always included, so there are never additional costs for new use cases you might use the tool for. And as already established, there are no user limits, meaning that once an organization has purchased a plan, everyone can access the software. Even further, as the pricing is usage based, the quota only gets consumed when the simulations are running, meaning that with the sporadic nature of simulation work, there will never be expensive licenses sitting idle when there isn't a need to run simulations. And when the simulation season is on, so to speak, the number of licenses or computational capacity will never be a bottleneck. In essence, we're all about providing our customers with the flexibility to choose what really best suits their needs. And also, something worth mentioning is that actually most of our customers started using AllSolve as an add-on to their existing tool stack. So instead of outright replacing the industry giants from the get-go, they initially adopted AllSolve for solving the simulations that were simply not possible with their existing tools. In acoustics, it's utilizing the possibility to run these giant third of a billion unknown simulations. And from there, many have realized that AllSolve can indeed handle all the rest too, and then have slowly begun discontinuing the expensive desktop-based licenses. For a more in-depth discussion on how Console and AllSolve can fit your specific need, I'll paste actually this link to the LinkedIn chat where you can book a time with our VP of Sales, Nicola, to explore what a potential collaboration could look like. But moving on, no need for expensive hardware, no need for updates. That is also no need to pay the electricity bill from a high cluster. Also, it is literally as simple as you have access from any device with an internet connection to world-class simulations. We have literally run these simulations using mobile phones. The last thing I want to touch here is the security, since many people with reason, I would say, are doubtful. Is the cloud secure? And I want to actually flip that around and to say that the security is not a weakness with the cloud providers, but actually a strength. So, based on a study made by Deloitte, they found that these mid-sized companies with ARR from 100 million to 1 billion spend typically 500,000 to 10 million a year on cybersecurity. Now, to compare to AWS, the cloud provider that we use, they spend a whopping 1.6 billion on cybersecurity per year. So basically, what that allows them to do is employ top tier security professionals that undergo rigorous security audits and get all the certifications that are out there. And of course, continuously update their security measures to to combat the ever evolving threats. Put short, these cloud providers typically have more sophisticated and robust security measures than most businesses can afford to implement on their own, simply because their business literally depends on being safe. With that being said, I just heard from Abhishek that the simulation has finished, actually some minutes ago. So I'll pass the mic back to Abhishek and let's see what we have there.
Thanks, Yukka. Yeah, Yukka already pointed out some of the benefits of cloud computing. Now, let's look at the results of our simulations. All three simulations have finished, and let's look at the logs. So the logs list out all the simulation progress. In this case, we have 100 pieces, almost 7.8 million degrees of freedom, and it took about 150 seconds, almost 2.5 minutes to finish this simulation. Now the absorbing boundary conditions, which are a bit lightweight, again 100 pieces, close to 7 million degrees of freedom, and they took about 82 seconds, so about close to 1.5 minutes. Lastly, the biggest simulations that we did today live, 105 million degrees of freedom on 500 cores. It took about 457 seconds, just about 7.5 minutes. So all three simulations finished. We finished simultaneously, or they were running simultaneously and finished within, let's say, 7 and 8 minutes. Now let's look at the visualization. So I would make some visualization of the harmonics, so pressure harmonic 2 on the surface that we created. So this is now downloading. As you can see, out of 500 pieces, only 279 are touching this surface, and that's you can imagine the huge amount of data that needs to be written for these big simulations, and that's why we chose to write only on surfaces, so that it's lightweight and easily visualized here in the browser. And in your simulations you would probably want to have such measures already before running the simulations, so that you don't have too much data which you would like to analyze later. Yes, so model is loading. Let me change the um, scales to visualize this better. 0.05, yes, apply, and you can see the pressure waves um, emanating on the surface, and we can also see them on this z plane that we created before. As you can see, there are two sources of pressure, basically sound, two loudspeakers which are emanating waves in radially outward direction. They are interacting with each other, causing interference, interacting with the objects inside the this living room, and yeah, basically, uh, and then leaving out of these PML boundaries or absorbing boundaries. Yes, so let's compare this with our lightweight simulation that we did. So here we used, for the big simulation, we used high order to get more accuracy, and compared to that with the lightweight simulation where we use second order for the pressure, we can have a look at the quality of the results or accuracy, and you can already see that with the lower order, the the quality of results is already um, not so good compared to the one with high order on the same mesh. So yeah, that's the advantage of using either the finer mesh um, or just increasing the order on the same mesh. mm, and you can clearly distinguish the difference in the accuracy of yeah, your computations. With this, I would like to hand over back to Yuka.
Very nice, very nice. Yeah, beautiful, beautiful simulation. Very, very impressive results. And again, we have the link right there in the chat. So indeed, if you want to learn more on how also could serve your needs specifically and learn more about the pricing, etc., Nicola is the person to talk to. And you can, for those interested, you can, for example, at this point, open it in a new tab and schedule a time right after the event. You can always find it too at our website, so quantsci.com/also. But with that being said, I think it's time for the Q&A session. So whatever you have in your mind, just type it into the chat, and let's see who's first. Well, I think there we have our first one from Andrew asking, can simulations include pro acoustic domains?
Yeah, thanks for the questions. So, in principle, I think we can handle different kinds of domains. If I understand your question correctly, the poroacoustic domain, you probably mean acoustics through porous materials, and that would include really small passages, if I'm right. And if that's correct, that would require, if you want to do it in all solve, you would require probably really fine mesh to mesh those small passages. But if you, I mean, yeah, definitely possible with if we manage to create the mesh through these passages, and we have designed our mesh refiner in such way that it takes care of these small scales large domains. So but do get
Sorry,
into the
Abhishek. It appears there's some issues with your microphone right now. Could you possibly check if there's anything you can do to perhaps even refresh or see if it's any physical problem with the microphone itself? Very very sorry about this. Of course, there has to be some technical difficulties, but hopefully we'll get them sorted very soon. In the meanwhile, actually, I could answer one of the questions that is we get often asked, since our company name is Quanscient. So the Quan, in fact, refers to quantum, or comes from quantum, which comes from the fact that at the same time that we are developing this cloud-based platform, we are actually doing, and these finite element method algorithms in there, these classical algorithms, we are also doing research in quantum algorithms. So we are basically doing research on how we can harness the power of quantum computers and utilize it in the multiphysics simulations. Currently, it is in the research phase, with most of the focus being in CFD simulations, where we have actually received some very promising results. We were, in fact, the first team in the world to solve a actual 1D advection diffusion problem using a real quantum computer, yielding actually accurate results. We published a blog post on our blog about that, and basically going over everything we have done on the quantum side from the past 2 years. So for anyone interested, it is out there. But to summarize, in the upcoming 5 to 7 years, being optimistic, we look to incorporate these quantum algorithms into our current cloud offering. So that sort of explains the Quan in quant science. But let's see if your microphone or connection has gotten any better.
Can you hear?
So yes, go
Can you hear
ahead.
me now? Hello. Can you hear me now?
Seems to continue. Seems to continue. Uh, all right. Well, what an unfortunate situation. There's a question from Per asking, how can the user make sure that he picks the right hardware for the choice? Is different hardware available for different simulation tasks? We'll have to wait for Abhishek to reappear for that one, but hopefully he'll come back soon. All right, Abhishek, are you back?
Can you hear me now?
Yes, seems to
Yeah.
be working.
Yeah. Sorry for. So my internet connection is not the best.
All
Uh,
right.
yeah, but as I was answering to that question on Puro acoustics, and yeah, it's principle definitely possible. Do get in touch with us to explore more your use case, and yeah, we can see if we can offer some solution. And next question I can see is from Per Matson. How can the user make you sure that he picks the right hardware for the choice? Is different hardware available for different simulation tasks? That's kind of so we make available all the hardware that's there, and yeah, I mean, you have to, what I can say is, you can first check, let's say, one iteration of your simulation, check the number of degrees of freedom, and then you get some idea how big your simulation is. So for example, rough thumb rule is, you should have at least 150 to 200,000 degrees of freedom for one core, and that gives some idea. So for example, when I did these simulations, I had like for 7 million degrees of freedom 100 cores, and that is about I guess 150 thousand tops. And uh, that's just the thumb rule. In some cases, for example, eigenmode analysis, you might need large memory, and for that you would use the biggest machine, for example 512 gigabytes of RAM and 32 cores. And yeah, those are kind of guidelines we can provide on usage of the machines or the hardware.
How about something again? Many people ask. Of course, is what does the training look like, or the support for new users? How does that work?
Yeah, so we offer, let's say, we have tutorial videos, all the documentation, um, and in addition to that, also we are also creating the written tutorials, for example, which would be available soon, for to step by step guides to create these simulations. And if there is a requirement on the training itself, we haven't thought of that, but we could offer in future some training sessions as well. uh, Otherwise, yeah, for the support we have free email support, so you can ask some basic we can solve your basic usage problems in that. And then we also offer priority support for paid customers. So there's different options available, but we can tailor that to your requirements. I can see one question here. uh, could you please tell us the different mesh models used? So um, I don't know what you mean by mesh models, but what I can say something about this is we use the tetrahedral mesh here, but that's not the limitation. We offer all kinds of support for all kinds of elements. And if you mean by different mesh models, importing other meshes, so yes, that's possible. We can import also other meshes from, for example, in Nastran format, and Gmesh format. So the basic mesher that we are using is Gmesh, so you can readily create meshes in Gmesh and upload them if you don't want to go through the steps. But we are also going to offer soon a mesh, directly importing mesh instead of geometry, if that answers your questions. Then next question I can see was the simulation performed in frequency domain or in time domain? If frequency domain was a direct or iterative linear solver. So the simulation was performed in frequency domain. We also offer transient option, but that takes quite long. So frequency option is probably the most suited here. Then yes, uh, it so we use direct solver. So we have due to cloud computing, we have access to huge rams, and that makes that enables us to use direct solvers instead of iterative solver, which is more robust in sense. And to just avoid the confusion, so about the iterations that you saw, the GM race iteration, those were for the domain decomposition method. So when we divide the domain into several pieces, each of these pieces solved on a separate core as a separate, let's say, finite element model itself, and it takes the boundary or the interfaces as the boundary conditions. And as you can imagine, each core solves its own domain, and then the solution at the interfaces should be somehow sync, should be matched. And that's where this iterative solver does for the domain interfaces. And yeah, uh, if that answers the question. um, then there is a comment. uh, could you show something where cloud computing has computational benefit? um, yeah, one thing I can say, I already said this. So we can enable direct solver because we have access to huge rams. And as you saw, we can scale it to hundreds and thousands of processors and enable large simulations, which might not be possible on um, desktop softwares, unless you have cluster uh, on your premises. But yeah, other benefits Yuka already mentioned about the security and stuff. um, One thing also I comes to mind is parametric sweeps. So this is kind of really trivially parallelizable. So you can run, for example, as I showed the frequency sweep, you can run them at the same time. So one simulation, for example, if takes 30 minutes, so you can run thousands of simulations and all will run at the same time, and you get your frequency sweep at the end of 30 minutes. So that's something that may not be possible without having the HPC resources or cloud computing. um, Reading on further, some kind requires several terabytes of memory, utilize at least thousands, preferably tens of thousands of cores. Doesn't have to be finished during the show, but very interest. Okay, whether this is even possible. Okay, so we have run so far. We have run up to, as far as I know, I personally have run up to 1,000 cores. We would really want to push the limits if there is a case available, and yeah, I would really recommend to get in touch with us to explore your use case and yeah, really see the limits of cloud computing that we can offer. And then behaves more complicated. Everyone does up to okay. uh, yeah, but I mean, you can imagine 500 cores, and if you have each of this has 500 gigabyte RAM, so that's easily quite large amount of RAM that's available. But yeah, I would recommend to get in touch. That's
Yes, we have time for one question from Damiano. If you answer fast to end
yeah,
within the time frame.
yeah. Do you currently support physical models like Pierce equation allowing count for mean flow effects? So we don't have this equation particular equation implemented, but as you saw the scripting, so you can implement anything, practically any equation in finite element weak form there. And yeah, so that's that should be possible, and if we see that there is requirement, we could also incorporate that in the GUI in future.
Perfect. Yeah. As the time is about to run out, we'll have to wrap it up. And thank you, Abhishek, for your answers and for guiding us through the demonstration. And of course, a big thank you to all of the audience for asking these excellent questions. And before ending, I just quickly like to summarize what we saw here, basically. So basically, if you are an acoustics engineer or in our other ways are dealing with these acoustic simulations, we know that the runtimes can be very long, even despite simplifying the models. And what we wanted to show here today is exactly that cloud computing, in practice, these cloud-based simulation platforms can be a viable and cost-efficient solution for not only solving these problems, but turning it into a strength. We saw in real time a 3D loudspeaker simulation with more than 100 million unknowns being solved in less than 10 minutes, which I think serves as a testament to the message we want to give out. Now, for the final time, if what you saw here resonated with you and you want to explore how Quansa and AutoSolve could expedite your workflows, or maybe you even want to get your hands on the tool, in any case, please use the link that's in the chat to open up Nicolas' calendar directly and feel free to book a time now for as soon as tomorrow. That being said, thank you once again, everyone. We really hope today's session has provided you with the answers you came here for. And we truly look forward to the opportunity to connect you again. So have a great day and take care. Bye bye.